here. It's now my pleasure to introduce Keith Knox, who is emeritus with the Air Force Research Lab, to take us into the next presentation.
Thank you very much. Yes, my name is Keith Knox. I'm with AFRL. 12 years ago, I came out to Maui, moved out to Maui, working with Boeing. Boeing's the prime contractor for running the Air Force site. You just heard how University of Hawaii and the Air Force have a very close relationship here on the island, and I'd like to give you a little instruction and overview of what the Air Force effort has been. 6 years ago, I moved over from Boeing into the AFRL and worked for 5 years as the technical advisor, as the lead scientist for the research going on for the Air Force effort. In January of this year, so 9 months ago, I retired from the Air Force, and Dr. Williams became the tech advisor. You might just raise your hand. So when you're looking for an opportunity to find out whether you can do some R&D together with the Air Force facility here, you should see Dr. Williams. You see there that I'm an emeritus. What that means is that I applied for the AFRL Emeritus program, which says that I can have access to a computer, a desk, an office, data, and come in anytime I want and do anything I want. They just don't pay me, that's all. But it's a lot of fun. So I'm going to give you an overview of the Air Force effort here now on SSA on the island. It's a joint R&D and ops site. We do both. In our operations effort, we are a contributing sensor to the SSN, which means we're not a dedicated sensor, so they don't just call us instantly. We respond as we can. But in that effort, we provide images of LEO satellites, and we provide metric data on geo satellites. We do simultaneously R&D, and we like to think, and we work these two together. We have the R&D effort and the ops effort working together, and we believe that in that way, the R&D helps the operations effort, and the operations help improve our R&D. And we've described that as our innovation engine for bringing SSA technologies to fruition quickly. So you've heard AMOS now several times. You see it up on the banner there as having one definition. The AMOS, as describing the Air Force facility, stands for Air Force Maui Optical and Supercomputing Site. We are both MHPCC and the observatory on top of the mountain. But AMOS started as something else. If you notice that in 1963, ARPA, which is the predecessor to DARPA, built a facility out here to observe missiles that were fired from Vandenberg going to Kwajalein. And so this was the ARPA mid-course observation station, because we were now here in the mid-course in between to be able to see those sites. And that's where the AMOS name came. Over the years, the AMOS name was just a very handy one to have. And so as the mission changed, the words changed in order to match the acronym. Here's a brief history of some of the things that have been accomplished here on this site. In '82, one of the first adaptive optics systems that was designed elsewhere and then brought and installed here was tested out and used. In '84, then the site transitioned from DARPA to the US Air Force. This is the Air Force, Space Command. And at that point, you noticed it was doing R&D up to that point. Here it developed a real operations mission through the Space Command and continued doing both R&D and ops. For example, the relay mirror experiment was conducted here on island. The first successful transmission of a laser from ground up to a mirror in orbit and then back down to ground. The High Performance Computing Center, which you just heard some things about, was established in 1993. The AOS telescope, the Advanced Electro-Optical Systems telescope, which is the main 3.6 meter telescope on top of the mountain, was built in 1999. And then Air Force Research Labs took over control of the site from the Space Command in 2000. And so now they're still, Space Command is still here on the site. They run geods. We are contributing sensor. We're providing information to them. The R&D is continuing. It's a big mixture of all those things going on, and it's a significant advantage, I think, for developing SSA capability. Here's a picture of the telescopes, the Air Force telescopes on top of the mountain. Of course, we're sitting on University of Hawaii land, and around us are University of Hawaii telescopes, not shown in this picture. But you can see several there, the 3.6 meter and a 1.6 meter, 1.2 meter, and then the geods domes. Here's a picture of the 3.6 meter telescope. I was always fascinated with this when I first saw it before I moved out here. I thought, why would anyone build a telescope that you have to raise up above the roof? It didn't need it. That was my first impression. Then I found out, no, the telescope is nice and firmly connected. They lower the roof around the telescope. And that leads to a very nice smooth flow of air across it. And so it becomes a very high resolution system. This one has adaptive optics on it. We also have 1.6 meter telescope. This is in a standard dome, and it's a smaller telescope. It's actually more versatile. It was built for tracking moving objects across the sky. And it's one that's our workhorse for daytime activities. The 3.6 meter telescope was built on top of a building which is octagonal in shape, and that gives rise to 7 different rooms that can be used for experiments. So that means that experiments can be set up in one of these rooms and then left there, and then somebody can come back and work. So it can be an ongoing experiment. It can be an experiment that is set up for a short period of time and then taken down. We can have several customers they're all working at once. The light comes into the telescope and then down 4 floors, and then in the center there gets right down here in the center, then gets directed off to one of the rooms or the other. So people can be sitting there waiting for their time to observe and then be ready and go. So now I'd like to give you a little brief description of the operational effort. The 3.6 meter telescope is adaptive optics. It's a high resolution imaging. We do high resolution images of LEO satellites. It has derotating systems, dispersion correction. It mainly operates in the terminator time period. That's when it's the best time that the adaptive optics is going to work. Adaptive optics doesn't work well in the daytime, so it's mainly used just for terminator imaging. This particular image shows the addition of adaptive optics imaging and some multi-frame blind deconvolution post-processing. Now, there's other kinds of post-processing, and that's, for example, like speckle imaging, which is totally post-processed. There's no adaptive optics applied to it. So what you see on the left is an image that you get when you do nothing to no correction to it. It's a big, fuzzy cotton ball blob. You take hundreds of those, work together on processing those, and you can produce the image on the right, which is the image of the satellite, which corresponds to the one on the left. This is the type of processing that we do in the daytime on the 1.6 meter telescope. And then in addition to those two, we have a number of small telescopes. You've heard the phrase Raven. That was a telescope that corresponds to a COTS around 0.4 meter telescope. And we have a number of those that we've used. We developed that capability for looking and getting autonomous measurements of metrics of satellites in GEO. We have high accuracy measurements with just this 0.4 millimeter telescope, 125 meters of GEO, which is around half an arc second. It's autonomously run. It can go down to 17th magnitude. It just sits there and runs and provides data to the network. Now, briefly, I'd like to talk about our R&D efforts. We're basically focused on 3 efforts: imaging, characterization, and detect and track, astrodynamics. I'm going to discuss 2 of these in some detail, but briefly, the imaging is resolved imagery, and it's mainly applied to LEO imaging, and the kind of research that we're doing today is to move this capability and more better into daytime area. Characterization is using non-resolved photometry to analyze the shape and attitude of satellites, or determine as best as you can what characteristics are of that satellite. That's an important area, and one that actually Paul Kervin leads in this effort, which is more and more important as we hear this. There's many, many more small satellites or farther away satellites that just cannot be resolved. And as part of that, we have a strong astrodynamics group that works on the problems of determining orbits and keeping track of the orbits. The main problem being the uncorrelated tracks, or UCTs, of all the different objects that aren't necessarily in the catalog, that you can't correlate to the catalog, and you see these tracks going, the spots going by, and you have to try and determine, is that an object? What other spot does it correspond to? And that's a tremendously computation-intensive problem, and one that has a lot of research on. So let me just talk a little bit now about the imaging, the one piece, and how it's evolved over the years. I just described how in 1982 we had one of the first adaptive optic systems on the 1.6. We also developed speckle imaging capability of taking images like you see on the bottom here, and taking hundreds of those to develop the image up on the top. If you correct it immediately with hardware, you can get an image like the one on the right. But in both cases, so this is the typical 1.6 meter telescope, this is the 3.6 meter telescope, but they both are coming from images like that. The effort that we've been doing over the time, those work well in the Terminator time period. Speckle imaging worked, I won't say worked well, worked in the daytime. And what our goal has been research over that time period is to move more and more of this capability into the daytime. And two things I'll briefly describe. One is aperture partitioning, which is very helpful for dealing with strong turbulence, and strong turbulence is what you're going to see in the daytime. And DORA is a SIBR project. I'll describe more about that. That's done by Hart Scientific. And again, it's addressing this problem of really bad turbulence in the daytime. So briefly, again, I just wanted to just put this up for people who may not be familiar with speckle imaging. You've got an object someplace, and you take a lot of short exposures. Because it's a short exposure, the atmosphere is frozen. And what it looks like is this kind of a random collection of dots. And if you take lots of pictures, each of these pictures is blurred with, the object is blurred with this random point spread function, producing these really fuzzy images of the object. But the one thing that all these things have in common is they were all made from the same object. And so the whole process of post-processing or speckle imaging or image reconstruction is to figure out what kind of object could have been used to make all these images that you see over here. And that's how you then you use methods there to recover what that object looks like. This is a movie of a rocket body, and this image was taken using their latest techniques on the 3.6 meter telescope. Excuse me, 3.6 meter telescope in the daytime. So this is a morning shot of this telescope, and post-processed in order to produce this image of the rocket body. So we're making great advances in our ability to get our telescopes to work better in the daytime. Aperture partitioning was another such example. This is a simulation where we're developing this for operational use as well. And the concept here is that if you take the full aperture and make an image and then try to recover the object from it, the spatial frequencies interfere with each other. And when you try to reconstruct, you get a fairly poor reconstruction. But if you divide the different spatial frequencies up by making these annular rings and measure them separately, and then process them, record them separately, but process them together, you can produce an image which is much higher quality than you can get from using the full aperture. So it requires splitting up your aperture, but you save all your light, and then you're able to recover a better result. So this is one of the major advances. This is something that Dr. Brandon Califf developed and is continuing to develop now for us. DORA is a Hart Scientific SIBR project, and their concept there was to use wavefront sensor data together with the images that were made. And their simulation shows that it can produce something quite good. This is what the image looks like originally. If you don't do anything to it, if you don't use this process, but rather just try to do normal reconstruction techniques, you get this kind of a blur. But by using the wavefront sensor data together with these images, they're able to produce a reasonable spot. And they're in the process now of developing this further for us and making good progress. I'd like to talk to you a little bit about the R&D, the ops, and I want to talk a little about how the ops and the R&D work together. We have the contributing sensor effort. We get questions asked of us of what's happening here. Can you help us understand? We bring our R&D people in to look and see what's going on. They can help us with the operations folks to answer some questions. And that leads to new concepts that the R&D folks hadn't thought of, and they start working on new devices, new sensors, new algorithms. And then they can, because they have access to the operational units, they can then do rapid testing of these concepts, and we can then apply them to operational units. This is the engine that we talk about, where we have our ops units help our R&D, and our R&D units help our ops. Just to give you some examples of that now real quickly, I want to show you how R&D has helped improve our ops, and that was done with the Raven effort, which ended up getting used in SPSS. The Raven developed out of work looking at asteroids in '95, and over the years we developed these autonomous systems that could find the satellite streaks automatically, figure out the metrics, provide the information, and then send this all off. And we do this routinely today. At the same time, people were developing systems that would be going into space and be doing space surveillance from there. And at the time that SPSS was being built, the space-based space surveillance system, satellite, was being built, they contracted Boeing, who were the same people who had built and developed the algorithms for the Raven. And so therefore, the algorithms and the research that was done here in order to create our Raven was then built into the SPSS satellite. And the SPS today runs on using the algorithms that we developed here for R&D. How does ops improve R&D? I want to talk a little bit about the effort when looking at uncorrelated tracks. Uncorrelated tracks are the real problem when you end up with something like the Iridium-Cosmos collision. You suddenly have thousands of new elements, objects that are appearing, and you have to try and figure out how all these things work. Debris is becoming more and more of a problem, and we have to face that. The difficulty is that if you're looking at radar, you see a whole bunch of little spikes. You've got these observations. Okay, great. And two of them together are probably an object going by, but which two do you combine? If we only had one object up there, it'd be easy. Every time I see it, I'll combine it together and make it an orbit. But when I've got thousands of objects up there, I'm going to see tens of thousands of observations. Which two do I combine together to try and make an orbit? It becomes a highly difficult computational problem. And a lot of this has a heavy manual component in it right now. Which means it just takes months and months to try and resolve some of these. And it's that need which was driving our work on looking at UCTs. And this gets even worse when you go to optical, because you need 6 scalars in order to get an orbit, and you get 3 from each observation in radar, 2 angles in a range. But you only get 2 angles you don't get a range parameter in the optical portion. So you need 3 observations. So that's an n cubed problem, not an n squared problem. So it's even worse for optical. We've worked together with the Naval Research Laboratory and folks at Dahlgren to take a look and see how this stuff is done today. We borrowed some of their software. There was a program called Search and Determine from the NRL. We borrowed their software, we parallelized it, we added the capability of looking at optical results. We made it run very quickly. We automated a lot of things. And this diagram just shows that given some data that was put in both optical and radar, we were able to recover all the objects that were known by looking at it by hand. And this last piece just shows SADI, which is this automatic UCT analysis program, is now being tested at Dahlgren. This is a quick test, shows the results of the test of using the Iridium Cosmos data. The Iridium Cosmos data was analyzed by hand. It took many, many months. They were able to find lots of objects and get the tracks. That data was then taken and fed back through into SADI to test out SADI. The data comes in not all at once, of course, it comes in over several days. So this is a plot showing the data that came on day 10, the data that came in on day 15, et cetera. That data was fed in a day at a time into SADI, and SADI was able to recover all of those objects in the 20-day time period rather than several months. So this is still under test, but SADI is showing that it looks like this may be the way to solve the UCT problem. So in summary, I want to describe AMOS, the Air Force effort here on site, the observatory on top of the mountain, the computing center down here on the coast. It's a joint R&D and ops site. We do both. The ops people benefit from having the R&D interactions. The R&D people benefit from interacting with the optics folks. And as a result, we're able to produce significant and rapid advances in SSA technologies. Thank you very much.